How old is the universe? How fast is it expanding? I mean, what is all that stuff out there actually made of?
Yeah, these are the big ones, right? The questions that keep cosmologists up at night.
Absolutely. And scientists are trying to get at them using some key numbers. There's the Hubble constant that tells us the expansion rate.
And the temperature of the cosmic microwave background radiation, the CMBR, that sort of faint echo from the very beginning.
These numbers are, well, they're fundamental, aren't they?
Oh, completely. Our whole story of the universe, its history, what's in it, really depends on getting those numbers right and knowing what they mean in our models.
So today, we're doing a deep dive that looks at these huge questions, but from a pretty different angle than the standard view.
Right. We're digging into a piece of research called Quintessentia Part 4 by Riccardo C. Storti.
And this builds on earlier work, Part 3, where the author introduced this method called electrogravimagnetics, EGM.
Exactly, EGM. The idea there in Part 3 was about representing fundamental particles harmonically, kind of finding a structure for them based on zero-point field equilibria, ZPF.
ZPF, like the baseline energy of empty space?
Sort of, yeah. And the really interesting claim from that earlier work was that this EGM method gave results for particles. Well, results that matched experiments way beyond what the standard model can currently calculate.
Okay, that's a big claim. So if it worked for particles,
Then the mission for this deep dive is to unpack how that same EGM method gets applied, scaled up to the whole universe.
right, how does it derive the Hubble constant, 8.0, and the CMBR temperature, T0, for today?
And crucially, what does that derivation tell us? What are the implications for the universe's history and, its actual composition? It's pretty fascinating stuff.
Okay, let's dive in. So section 1, setting the stage.
Yeah.
How do you go from tiny particles to the entire cosmos
Right.
using this EGM idea?
Well, the EGM method, as laid out before, uses these standard physics tools like dimensional analysis, Buckingham pi theory, to represent systems harmonically. It's all centered around this ZPF equilibrium concept.
Finding these underlying patterns, harmonies in mass and energy.
Exactly. And Part 3 seemed to show that for particles, mass energy distribution follows, like just one specific pattern in this EGM framework.
Okay.
So Part 4 makes the jump. It applies those same principles, the harmonic mass energy distribution, the idea of similitude or similarity, based on ZPF equilibrium, but now to the universe as a whole.
Similitude. So, like looking for scaling laws.
Yeah.
Similarities between the very small and the very large.
That's the core idea, yeah. And they set up the comparison using two key analogies.
Analogies for the universe.
Right. First, the primordial universe. Think of the state just before the Big Bang.
Okay.
In this model, it's represented as a kind of idealized particle, homogeneous, at the Planck scale, the tiniest possible scale with the maximum possible energy density.
A single Planck scale particle for the whole early universe.
And it's characterized by a single EGM wave function. They see it as analogous to a Schwarzschild black hole, theoretically.
That's quite an image. A Planck scale black hole state. What's the second analogy?
The second one is our own Milky Way galaxy. It's also represented as a Planck scale object.
Wait, the whole galaxy is a tiny Planck object?
Yeah, but one whose total mass is equivalent to the estimated total mass of the Milky Way. They call this the galactic reference particle, or GRP.
Right.
And unlike the primordial particle with its single wave function, this GRP, representing the complex galaxy, is described by a huge number of EGM wave functions.
So, two simplified Planck scale things. One for the very beginning, one for our galaxy now, represented by the GRP. What then? How do you compare them?
That's the core method. A comparative analysis similitude between the primordial universe representation and the Milky Way GRP representation. And they use the same harmonic equation that was developed for particles in Part 3.
The same equation. Okay. And what goes into that comparison?
Known values related to us here, like the average distance from the sun to the galactic center, rho, and estimates for the Milky Way's total mass, mg.
And why use our solar system's location as the reference point for the GRP?
Well, the paper argues it's practical. That's where we actually are when we physically measure things like the Hubble constant. Makes sense?
Yeah, okay, that's logical. But I'm still trying to get my head around how comparing these two tiny theoretical things using a particle physics equation gives you the expansion rate for the whole cosmos today.
Well, the assumption in EGM is that these fundamental harmonic relationships, these scaling laws, they hold across vastly different scales. So by comparing the properties derived from the primordial universe representation and the Milky Way GRP representation within that EGM harmonic equation, The math yields the Hubble constant.
Ah, okay, so AGO pops out, initially defined using terms related to our galaxy's size and mass.
Exactly. It finds this mathematical bridge between our local galactic environment, as modeled by the GRP, and the overall cosmic expansion, all governed by these EGM principles.
Fascinating. And the CMBR temperature, T0, how does that emerge?
That's derived from the Hubble constant value they just found. It's not independent.
So T0 depends on H0 in this model.
Yes. The derivation involves calculating a theoretical frequency shift. Imagine an EGM wave function being radiated from that primordial particle analogy. Calculating its shift gives you the temperature, T0, directly in terms of the H0 they derived.
So the background temperature is basically a direct result of the expansion rate itself, not described by typical thermal physics.
That seems to be the implication, yes. It's quite different.
So what numbers did this EGM process actually spit out?
Okay, the derived Hubble constant, they label it HU2, is about 67.0843 kilometers per second per megaparsec.
67.08. That's right, smack in the middle of the current observational tension, isn't it, between the different measurement methods?
It is, which is definitely noteworthy. And the derived CMBR temperature, TU2, comes out as approximately 2.724752 Kelvin.
Well, okay, 2.724752 K. That's incredibly specific. The measured value is super precise too, right?
Exactly. And this is where the paper highlights something it considers, well, pretty remarkable.
What's that?
Applying this EGM method to cosmology inherently reproduces the characteristics of a black body radiation curve.
Okay, like the CMBR spectrum.
Yes, but here's the kicker. It does this without explicitly putting in the standard black body law from physics.
Wait, really? It gets the black body shape without using the black body formula.
Apparently so. That's the claim. That the black body nature emerges from the EGM framework itself when applied to the cosmos.
That is interesting because the CMBR is famously the most perfect black body spectrum we've ever seen. If this EGM approach gets that right, sort of fundamentally.
It's a strong point for the model, yeah.
Oh.
And they stress how incredibly close their derived value, 2.724752 K, is to the experimental measurement, which is what? 2.725 plus or minus 0.001 K.
Time tolerant.
Tiny. So the argument is, look, getting a theoretical value that close within such tight experimental limits using this completely different approach, you should probably pay attention.
Hitting the temperature that precisely, linking it to H0 in the ZPF, yeah, that definitely makes you pause. Did using that measured temperature then help them refine the galactic inputs they used?
It did, yes. They sort of ran the calculation backwards. By plugging in the measured T0, the 2.725 K, the EGM model then gives improved estimates for the Milky Way properties.
Ah, okay. Like what?
The distance to the galactic center, R0, gets refined to about 8.1072 kiloparsecs, and the Milky Way's total mass, mg, to about 6.3142 times 10 to the 11 solar masses. These are pretty reasonable numbers astrophysically.
So it's self-consistent. The model gives results matching data, and the data helps refine the model's inputs. Okay, now the big implications. If this EGM picture holds, how does it change what the universe is made of and how it expands? This sounds like where it really diverges.
It really does. This is where things get, let's say, dramatically different from the standard lambda CDM model. Take dark matter and dark energy.
Yeah, the big mystery is making up supposedly 95% of everything.
Right. Well, the EGM derivation of H0 and T0, according to the paper, mathematically demonstrates that the effect of anything you might call dark matter or dark energy on these specific values is less than 1%.
Less than 1%.
Yeah.
But standard cosmology says they dominate. How can their influence be negligible in this EGM framework?
It's a huge contrast. It leads to a completely different recipe for the universe. According to EGM,
All right.
over 94.4% photons.
The photons, light particles.
Yep, over 94.4%. Then, less than 1% attributed to dark matter, dark energy effects, and the familiar stuff, atoms, make up the remaining 4.6%.
Okay, hold on. Standard model, 72% dark energy, 23% dark matter, 4.6% atoms. EGM, 94% photons, 1% dark stuff, 4.6% atoms. Where does all the gravity and expansion effect go? How can photons account for what we attribute to dark matter and dark energy?
This is maybe the most radical part. The EGM perspective argues that most of what we currently call dark matter and dark energy is fundamentally just photons. Because within the EGM construct, the graviton, the hypothetical particle carrying the force of gravity, is actually defined as coherent groups of conjugate photon pairs.
So gravity itself is intrinsically linked to photons in this model. And the effects we see, like galaxy rotation curves or cosmic acceleration, that we thought needed dark matter and dark energy, EGM says it's actually photon behavior, described by their graviton definition.
That's the essence of it. It's a fundamental reinterpretation. And it extends to the accelerated expansion, too.
Right, the observation that the expansion is speeding up. Standard model says dark energy is pushing everything apart. What does EGM say?
EGM attributes accelerated expansion to the nature of the vacuum itself, specifically the zero-point field energy density threshold.
ZPF again.
Yes, their derivation requires this baseline energy density of space to be negative. Less than minus 2.52 times 10 to the minus 13 Pascal specifically.
Negative energy density for empty space. That sounds weird.
Yeah.
How does that drive acceleration?
The paper links this negative ZPF energy threshold directly to the dynamics predicted by the EGM equations. It's not entirely intuitive from a classical standpoint, but within their mathematical framework, this negative value leads to the observed effect. They also point out that their model predicts the rate of change of the Hubble constant over time is currently positive. That's just the mathematical signature of acceleration.
So instead of adding a mysterious dark energy fluid with negative pressure, EGM suggests the acceleration is an inherent consequence of the vacuum having this specific negative energy property within its own framework.
Exactly. It's baked into the fundamental structure of space-time as described by EGM, rather than being an added ingredient. It's a very different way of looking at it.
It really is. And does this framework also sketch out a different history of the universe based on these derived H0 and T0 values?
Yes, it does. It lays out a specific thermodynamic and expansion history right from the Big Bang event up to today.
How does that timeline look in the EGM picture? Is it broken into stages?
It is. They categorize cosmic evolution into two broad regimes, called non-physical and physical. And within those, there are four distinct periods: primordial inflation, thermal inflation, Hubble inflation, and finally, Hubble expansion, which we're in now.
And what defines these periods?
Basically, how the temperature behaves and how the magnitude of the Hubble constant changes over cosmic time, according to the EGM model's calculations.
Can you give us just a couple of key moments or snapshots from that EGM history?
Sure. At the very instant of the Big Bang, the model calculates an incredibly huge Hubble constant, like 10 to the 61 kilometers MPC. But interestingly, a temperature of absolute zero Kelvin.
Zero temperature at the bang. That's counterintuitive.
It is, in this specific model's definition of that initial instant. Much later, it calculates a moment of maximum cosmological temperature, reaching something like 3.2 times 10 to the 31 Kelvin, an incredibly hot, dense phase.
Wow.
And then, of course, it evolves to the present day, characterized by the derived temperature near 2.725 K and the Hubble constant around 67 kilometers MPC that we discussed.
It's really something how this single EGM method, starting from particles in the vacuum, builds this whole alternative, self-consistent story for the universe. Its contents, its expansion, its history that looks so radically different from the standard picture.
Yeah, what's really striking is the attempt to forge this direct link, connecting the physics of the very small, where it claims some success, directly to the largest scales and biggest mysteries in cosmology.
Which really brings us to the final point. Why should you, listening now, care about digging into this particular deep dive, this EGM perspective?
Well, because it gives you a chance pretty quickly to get your head around a completely different way of thinking about the universe.
Right, a framework that tries to unify particle physics with cosmology in a very unique way.
Exactly. And it might give you some of those aha, or maybe, wait, what? Moments, like the idea the universe could be, well, overwhelmingly made of light particles, photons, instead of mysterious dark components.
Or that maybe the reason expansion is speeding up isn't some dark energy force, but something fundamental about the energy of empty space itself being negative.
Precisely. It's about gaining some insight, quickly but hopefully thoroughly, into an unconventional approach, one that really challenges the standard cosmological model and offers this, well, unique angle on fundamental cosmic questions.
Though recapping our deep dive, we've explored how this electrogravimagnetics, or EGM method, building on work in particle physics, is applied to the whole cosmos.
Yeah, deriving the present-day Hubble constant and CMBR temperature, and notably getting a temperature value right on the money experimentally without even needing the standard black-body law.
And we looked at the really surprising consequences. An EGM universe composed mostly of photons, 94%, with dark matter and energy playing almost no role, 1%.
A huge departure from the standard model. Plus a specific explanation for accelerated expansion tied to this idea of a negative zero-point field energy density for the vacuum.
It definitely paints a different picture of reality. So, here's a final thought, something for you to chew on. What if that vast emptiness of space isn't really empty? What if it's a dynamic field defined by fundamental properties, like maybe a negative energy density?
And following that, what if the missing 95% of the universe we've been searching for isn't some exotic dark matter or dark energy particle, but is somehow just different states or manifestations of light itself, of photons governed by principles like EGM?
Lots to think about. Keep learning, keep questioning.